This is a joint discussion with NVIDIA, HPC middleware research and development group with Facebook, AI infrastructure team. I'll let the Facebook team introduce themselves and tell a little bit of background about what their mission statement is within Facebook. Our mission statement within NVIDIA and previously at Mellanox, my group is broadly responsible for the design and implementation and really ultimately the deployment into production of Mellanox's HPC middleware. So that includes, traditionally it's been, HPCX, so MPI, OpenSHMEM, and then the associated accelerators underneath those, UCX, Sharp, and HCall Collective's communication library. I'll kick this slide off, Srinivas, and if you want to pop, you can tie into it if you want. So what's next with collective communications from my perspective in my group and from Mellanox and NVIDIA perspective. So, we've been developing collective communication libraries for the world's biggest supercomputers. It sort of culminated with the deployment of Summit and Sierra and the HCall collective communication library being used in the context of the collective's backend for Spectrum MPI and using HCall to achieve the acceptance numbers on Summit and Sierra. That effort took, from conception of HCall, which started off as Cheetah at Ornell with a group of individuals here with Pasha and Manju, myself, Rich Graham, Steve Poole, and Gilad, and some legacy folks from Mellanox. 10 years ago, we started on what would eventually become HCall. It went through a whole life cycle in industry, being hardened, extended, performance, optimized, and then ultimately deployed on, the sort of its big moment being installed as enterprise class software on Summit and Sierra for acceptance testing. So, we put together HCall as a library targeting like 100 petaflop system, and we kind of designed it on Jaguar, which was like a 5 petaflop system. And so in 10 years later, went through this whole life cycle and was actually, then installed and is the production grade collective communication library on Summit and Sierra, which is like a, order 100 petaflop system. So HCall, lived its full life. And now HCall is at the end of life, much in the same way that MXM was at the end of its life, sort of was one of the impetus drivers for starting UCX within Mellanox, so it could replace MXM as a closed source proprietary library. The goal here is to do the same thing with HCall, which is take our, sort of all the lessons that we've learned over 10 years, developing collective communications for, the world's fastest supercomputers and doing, pushing this into the open source and doing the same thing for UCC that we did for UCX in the context of MXM. So taking the proprietary libraries that we had, kind of breaking them open, taking the lessons that we learned and putting them into the open source. That being said, so, HCall's at the end of life. UCC is the next generation communication, collectives communication framework, and really the frameworks that are consumers of collective libraries are quite different than they were 10 years ago, and the architectures are quite different. And so we went about, trying to keep always in mind that, we want to be, if we're doing, UCC, we want to be at the cutting edge with respect to making sure that the API is suitable for, the cutting edge frameworks, and that, there's actually a demand and that's actually meeting a need that's out there. And so I think, PyTorch is certainly an obvious target, right, for wanting to co-design not only UCC from the ground up, but what's interesting is that, unlike MPI, where, a lot of the applications and the frameworks that are riding on top of the acceleration libraries, even if it's MPI, MPI is written in stone, right? And the Fortran applications that are running on top of MPI are hardened in cement. They're old legacy applications. There's not a lot of room to move around. What's really exciting about this effort is that, all of these deep learning, machine learning frameworks are so new and evolving and emerging, and sort of, there's still some plasticity in the actual framework development. And so developing a new communication framework in parallel with that, with those efforts going on, if we can co-design together, it's a really interesting opportunity to, sort of help shape what the look and feel of UCC will end up becoming, and how, it can really, how it can become, how it can actually be effectively deployed and adopted for mission critical settings, right? So, I mean, the goal here is to get this into the hands of consumers who want to, scale their clusters and their workloads to the biggest scale possible. Srinivas, did you want to?
Josh, this is a good introduction.
Okay.
I'll jump in later.
Sure. And so the technical team, Srinivas and I, we were brought together by solutions architect Elad Wind in Mellanox, working together with Srinivas and Dimitri and Peter. And I think, they were looking at collective community, and I'll let Facebook, explain what their needs were. But they had a problem that needed solving, and we had a problem that needed solving as well, or we needed, we were looking for a problem, let's say maybe to help steer the development of UCC beyond something more than just MPI, because we have a lot of experience with MPI, we have a lot of experience with PGAS languages, and we have some experience with deep learning frameworks, but being able to actually co-design UCC with, something like DLRM as a first-class citizen consumer framework was really an awesome opportunity here. So this is my team here. So this is everybody that's really committed to the project. I mean, we've got, like I said, we've put our money where our mouth is. I'm fully committed to this because I don't have an HCall library that I'm actively developing now. So any new feature development or feature exposure for new hardware, for example, NDR generation hardware, like all the feature development that's going to happen has to happen in the context of UCC. We're not going to do anything with HCall. HCall's at end of life. We're putting it out to pasture. It's going to go retire and fish on the lake somewhere. So for us, it's critical that UCC has a path forward to a space in production environments. And with that being said, Srinivas, you want to introduce your team and talk about what you guys do and how this all fits in with your work?
Sure. Thanks, Josh. Thanks for the introduction. Seems like I didn't do my homework and share my bio, but very briefly, I'm Srinivas. I am the AI networking lead within the AI hardware software co-design team in Facebook. As the name suggests, this team is kind of the bridge between the software, the workloads, and the hardware side. This is a highly cross-function collaborative effort within Facebook across various teams and folks, including Pallab from CEA, Peter from NetEng, Dimitri, who is a TPM, and Ching and Misha from my team, Misha being the director of our team. And overall, this effort, like Josh laid out, is an important effort for Facebook, and a serious collaboration between Facebook and NVIDIA to co-design the communication library and PyTorch and systems for AI training. Next slide. And like I was saying, there are a couple of these things that we are that are key to the work we are doing in Facebook, key to AI training in production. It's this, and UCC is exactly in the intersection of all these different pieces, including AI workloads and benchmarks, communication library, and distributed PyTorch. And we really see UCC being able to deliver this, a unified communication library for all AI training needs. And this collaboration, again, with NVIDIA and the work we'll be talking about today is kind of a proof point towards us moving in that right path, towards moving towards a North Star for us, which is being able to deploy a single PyTorch implementation of a communication library, with the communication library providing various performance across CPUs, GPUs, and various devices. So that's kind of the nutshell of this work that we are doing and the direction we are marching towards. So I'm going to quickly talk about some of the some aspects of the workload, some aspects of PyTorch to give folks a quick overview of the state of the union here, and let Josh take over and present the details of the work that we've been doing and the next steps, so on and so forth. So I don't think I need to convince anyone here or in any group, I guess, now that the importance of AI and machine learning, given the rate of growth. This diagram shows the standard ML pipeline we use in Facebook for AI training, starting from data and feature extraction on the left to training and evaluation, and finally deployment. As you can see, this is a highly feedback-driven loop, and the growth of some of this within Facebook has been phenomenal in the last few years. At the beginning of 2018, for instance, if you just look at the numbers, 30 warehouse was used in the ML pipeline. In 2019, this is not today, this is in 2019. In 2019, that 30% of the data became 50%. We were using 50% of the data used in warehouse, right? This, along with the fact that the warehouse size has doubled year over year, essentially means that just the amount of data that we use for AI training has kind of tripled over that 1 year period, right? And it continues to grow as we have been moving forward. Also, in terms of the number of engineers involved, the workloads, the compute, and all those metrics also have seen significant growth. All this feeding into various inference use cases, which end users land up seeing, which could be a number of predictions, translation of information, or even hate speech, fake accounts, so on and so forth. So this topic, kind of the AI training pipeline is a key workload for us and workflow for us, and all this growth adds a significant burden on our infrastructure. Next slide. Digging deep, one step lower, and looking specifically at what models. In our case, recommendation models are highly critical for Facebook. Of tasks, including ranking and personalization. And very simply, these recommendation models help kind of choose, recommend a small set of items to the user from a large set. And this shows up in ads or news feeds or various other practical applications that we use in Facebook. These models are different from some of the typical AI workloads, like different compute and communication behavior, which I'll talk about shortly. But the crux of the problem statement here is to take a set of features, maybe which characterize users or ads, and produce a probability that the user will choose the item. And many of these features that we talk about here are categorical features, which means that there is a finite set of categories with a discrete set of values. And the AI training job is to figure out what those numerical values are. But in effect, what you see here is the growth of this workload somewhere in 2018, 2019 timeframe, to show how much of our, the importance and the growth of this workload within Facebook AI workflow. And kind of comparing against CV and NLP, like I mentioned earlier, CV and NLP workloads, they typically gain a ton of press or coverage in academic papers, but these are different from the DLRM, which is deep learning recommendation models that which drive this work. CV and NLP models typically have smaller compute, are smaller and compute intensive, and more flops driven. The communication behavior is typically an all reduce given data parallelism, but recommendation models have this, have very high memory capacity requirements, which means that they need to scale and have high network and I/O requirements, which essentially makes them more communication bound than the typical CV and NLP workloads. Next file. You could get the whole thing out. So the Facebook had released a benchmark a year or two ago called Deep Learning Recommendation Model Benchmark, which represents many of the key aspects of representative of internal workloads. And as you can see, they have a very good combination of compute, I/O, networking, storage, and stress different aspects of these things in different parts of the workload. Recently, DLRM was made part of MLPerf, so it's been an official benchmark as part of MLPerf. But the interesting piece for DLRM specifically is this core problem of trying to deal with these categorical features I talked about. How do you kind of, how do you kind of learn the numerical values for these categorical features, and unlike typical CAV or NLP, the core compute here, or the core representative thing here, is the embedding table. Embedding tables are these large distributed tables that span not just one CPU or one GPU, but tens or hundreds of these CPUs and GPUs. And in essence, involves doing distributed table lookup and update operations across tens or hundreds of these devices. And in addition to the all reduce that we know in AI training, these distributed embedding tables essentially introduce these large all-to-all collective operations that significantly stress the network. We also want this flexibility of being able to deal with CPU tensors, GPU tensors, in a sense that if you want to do CPU training, be able to do all-to-all all reduce from the CPU. If you do GPU training, be able to do that from the GPU, or even with GPU training, have the flexibility in some cases to say that the communication library should support collectives for tensors sitting on the CPU instead of moving them into the GPU first. So, set of requirements from the workload for us, and essentially kind of sets the stage for the work that we are doing with respect to UCC.
Hey,
So
Srinivas,
I'm going to shift.
do you mind if I ask a question now or later?
Please go ahead.
So do you see like in your workloads and your usage moving from say CPU-based collectives to DPU-based collectives and using intermediately, or in a model you have is where you use a GPU model or a CPU model? It's one or the other, or is it exclusive, or you mix and match also?
So I think one of the things that we are exploring today, and I'll get into more details. I think one of the challenges that we have today is that we don't have a single communication library that supports both. And hopefully UCC would be that communication library that supports both these different types of collectives, or rather something in CPU memory, something in GPU memory, and you would want to do. We do have a requirement, or performance benefits of supporting high performance collectives in a hybrid manner. When I say hybrid here, I just want to mean that it might, we might have a case where there is a collective between CPUs, there is a collective between GPUs. That could be also a case where, maybe for instance, an all-to-all, right? And this is something we are exploring with DLRM, is the source of the all-to-all. Source buffer of the all-to-all could be CPU, the destination buffer could be a GPU, right? So I think, yes, the short answer is that we are looking for a very rich set of collectives, even within a single training job, to be single training job.
Thanks.
I have another question. I will use opportunities that somebody already interrupted. In terms of point-to-point communication, do you guys care at all about point-to-point? And if you care, what abstraction you use for point-to-point communication?
Yeah, I'll talk about the next couple of slides, talk about the abstraction, but from a workload perspective, yes, so I think I'll kind of answer this question in two levels. So if you look at AI training in general today, it has been kind of focused on all reduce a lot, primarily because data parallelism, what really helped scaling until recently was data parallelism, and data parallelism requires an all reduce where you replicate the model across each device, and you need to do a gradient synchronization, and that maps very well to an all reduce, right? So that regime of scaling, all it requires is all reduce. But if you really see kind of the scaling challenges or various papers as well as whatnot, we are beginning to hit some of the limits of data parallelism, or in some cases require more sophisticated parallelism techniques like model parallelism, which introduces more collectives than just an all reduce. The embedding table, distributed embedding table lookup, an update I talked about, is essentially effect of model parallelism, because all tables cannot fit within one GPU, so you need to distribute it. There's no replication of these tables. That's one instance of all-to-all. However, there are versions of model parallelism where you need point-to-point support as well, right? So when we move from data parallelism into model parallelism, not just for recommendation models, but across a lot of the AI training workloads, you will begin to see a richer set of semantics or collective communication library communication operations required across the board.
Thank you. And we have one more pending question in the chat, so I will use the opportunity to read it out. What is a typical message size you see for DLRM, all reduce, and all-to-all?
Right. I think what we have published in terms of ML-perf models are typically much smaller than what we do internally. Similar to a lot of the AI training workloads, our all reduce sizes are large all reduce, tens or hundreds of megabytes, depending on the specific model that we talk about.
And growing, right? I mean, it's
and growing.
growing.
The all-to-all is essentially a function of the batch size, the embedding table, so on and so forth. And even that is growing. And I would kind of say for all-to-all, hundreds of kilobytes to few megabytes per peer, right? So multiplied by the number of peers or number of devices that you talk to, but per device you are doing hundreds of kilobytes to 1 MB, which is essentially a large all-to-all, which is what I mean by a large all-to-all.
Thank you.
All right, so that I think that sets up the stage for the workloads and kind of where things are going. I think the key glue from Facebook or even the is the AI training frameworks, and PyTorch is something that is one of the fastest growing AI framework, deep learning framework in use in the industry today, and it's an open source framework with tons of users. And kind of one of the core aspects of PyTorch is this simplicity of being able to get it up and running, and if you really look at a lot of the AI training or even papers and whatnot, you can clearly see academics or anybody trying to just download PyTorch, running it on their GPUs or CPUs, being able to scale it within a box or within a couple of very quickly, right? And I think that core, we want to kind of have that core aspect of feature in mind of simplicity and productivity, and lower the bar on being able to scale some of these workloads going into the future. Next foil. And I think Pavel had a question on the interface, and so this diagram, this figure essentially kind of gives a high-level overview of PyTorch, and very specifically the multi-node or the distributed aspect of PyTorch. So coming top down, you have the applications or workloads benchmarks sitting on top of the PyTorch user-facing API. And under it, you have, under PyTorch, you have what's called a process group interface. There are a few different ways you could do distributed PyTorch. I'm specifically talking about the things that we use for synchronous training, and kind of the things that we are working under the UCC umbrella right now. And in the process group interface is kind of that abstract interface, collective and point-to-point interface that essentially provides a device-agnostic portable API to separate the different implementations, communication libraries, whatnot, from the core PyTorch, right? So that interface is essentially what what is being exposed within PyTorch. And today, if you look at PyTorch, there are multiple implementations of this interface. That is Nickel, Glue, and MPI. All these have been upstreamed as part of PyTorch. Especially the Nickel process group is the one that's typically used to scale on GPUs. And each one of these implementations, process group implementations, is backed by the a third-party communication library, or in the case of Facebook's own Glue communication library, to implement the various collective operations and point-to-point operations. But essentially, there already exist the the key takeaway here is that already exists a device agnostic collective and point-to-point API and multiple implementations of this API today. Next slide. But one of the things that we are seeing with these implementations today, is this is a snapshot of the support from different from one of the documents. This is probably a bit outdated because Nickel supports point-to-point and all-to-all, but the large, the bigger essence of this is that we don't have a single process group implementation, and primarily because we don't have a single communication library that uniformly supports collectives and point-to-point operations in a manner across CPUs, GPUs, and many other devices, right? That does not exist today, and and this is where we really see UCC being that communication library interface, where you can imagine a vertical here which says UCC, and from PyTorch process group having a single PyTorch process group based on UCC, being able to essentially check all these different collective and point-to-point operations. And so that's kind of our North Star here. So if you kind of look here, we have, what we are working towards in close collaboration with Josh and his team is essentially this idea that, have a, what's called a PyTorch UCC process group, also called, referred to as Torch UCC, but, and implementing and providing that full feature capability across CPUs, GPUs, and being able to mix and match, right? Because from a process group interface, all you deal with is tensors and collective operations, right? You can introspect the tensor and say, okay, is it a CPU tensor or a GPU tensor, and then call the corresponding collective. That ability to have that full feature is lacking today, and this work that we are collaborating on is to deliver that capability in line with a lot of the PyTorch principles, which is out-of-box performance, portability, and robustness across platforms, and more importantly, deploying this code in Facebook AI training systems in production. I think that's kind of our North Star here, to demonstrate the one-stop solution for us to do that. Any questions on the?
Hi, Srinivas, this is Pavan. I was just wondering, that you had a column for MPI as well. So I was wondering what additional features you like functionality-wise, not performance is a different story, but functionality-wise, I was curious as to what you think would be added by moving to UCP plus UCC combination.
From an API perspective, when you say functionality, you mean primarily from
API capability. Performance is a different story.
I think, yeah. Can you please repeat your question? The last part.
I was saying that the last part was essentially I was saying performance is a different story, and I can totally see a case for performance improvement. My question was more towards just a functionality difference.
Right. So I think that's a great question, and stepping back a bit, not even looking at this thing. I think if you look at Glue or Nickel, even, I think a lot of the functionality has been driven by MPI, right? This idea of collective APIs and whatnot, right? So a lot of that has already been driven by MPI. So from a functionality perspective, I think MPI is, supports many of the features that we are looking for already. I think one feature which, thinking about it, one feature that would be beneficial to support an MPI, which I believe is supported now in the persistent process group work, is unordered collectives, right? Having the flexibility to do unordered collectives, to be able to schedule the collectives in a manner that is more in line with the AI training requirements, which is essentially a LIFO ordering. So if you look at the back propagation step of AI training, which is where pretty much a lot of the collective communication happens, in a typical data parallel workload, you have all reduce operations being issued in one order, but the expectation of completion is kind of in the reverse order. It's a LIFO ordering.
Right.
So
yeah,
I think,
I'm aware of your that work. I think you did that while you were in Intel earlier, right? So I'm aware of that part. But my question was, I think we should take this offline. So I don't want to take up too much time here. Thank you for the answer.
Absolutely, yeah, we can definitely chat. All right, so I think just to kind of set the I just mentioned what the North Star for us is to have a single process group to be able to drive the in line with a lot of the larger PyTorch themes of simplicity and robustness. That's where I want to kind of close on this. Next file. So one of the things that we've been doing on the PyTorch side, or at least on the benchmarking side, in addition to DLRM, is this set of micro benchmarks or compute communication benchmarks that we released recently called Param. And Param Comms is essentially these AI training communication benchmarks that we've been using, and we released recently, and Param Comms essentially is again a PyTorch based communication benchmark, which relies essentially on PyTorch interfaces and hence the process group to provide device agnostic, platform agnostic, collective communication library or collective communication benchmark. And one of the nice things about using Param is that it is in line with either nickel test or OSU Intel MPI benchmarks, in that it provides this blocking, non-blocking collective type operations and single collective micro benchmarks, but it also captures this DLRM communication behavior, which is kind of the communication that happens in the forward and the backward passes of AI training, without having the compute features. And this thing allows us to kind of test different to test communication in isolation with compared to a lot of the other standalone collective benchmarks. So this is again something that we are using as part of this work to evaluate UCC, and we are already seeing some very good results. I will let Josh kind of talk about UCC and all the other work we have been doing.
You want to summarize this is in a nutshell, Srinivas, why UCC? I mean, if I'm hearing what Srinivas just said, just to sort of summarize it to the audience as I understand, right? So want to support a single PyTorch process group that can support CPU, GPU, and DPU transparently. Leverage UCX building blocks, right? I mean, one of the reasons why we've been able to sort of bootstrap this so quickly and get this, to extreme scale rapidly is because we're already starting off, on a foundation between UCX, HCAL. I mean, there's a lot of institutional knowledge and mileage baked into the project already that we inherit. So it kind of feels like, oh, we're moving so quick, we're doing this, we're doing that. But, it's because now those investments are starting to really, we're getting sort of a compounded interest, it's compounding return on our investment in UCX and HCAL over those years, and being able to, leverage this in this fashion and get this deployed at data scale, internet scale, and you know, it's not a toy. You have highly stable pieces that have already been, you know, in the wild, in production for quite a long time, doing very, very extreme things. You know, it's a vehicle, we can use it as a vehicle for hardware, software co-design. It's adaptable, flexible, extensible, future-proof, and it's open source and community driven as well. So, you know, it's not, you know, you don't have a single point of failure. You have, you know, you're leveraging the institutional knowledge of everybody in this community, the academic, the national labs, all of the vendor support and user community that actually use this, that use these things, like that have given talks previously, like with NAMD and so on and so forth. But you know, I mean, there's, I think having the support of the community and the, you know, the ability to drive big things forward in a reasonable time frame was also, you know, part of the choice, I guess. So Facebook has laid out, you know, the case and the problem, sort of teed up the problem, right? So we want one-stop shop communication framework to support a single PyTorch process group in our AI data center infrastructure. So we marched together arm in arm in this collaboration to see what we could do quickly and see if we could demonstrate proof of concept and then make some, you know, go, no-go decisions based on that, both from both organizations' perspective. So from Facebook perspective, go, no-go with, you know, UCX or UCC, does it make sense to continue investing in this path, or is this just, you know, kind of nice idea, but, you know, maybe when it's not quite ready for prime time. And then from our, you know, from our perspective, you know, making sure that, that, you know, we would actually have an API, a UCC, the API actually does, you know, sort of what our objectives were in the very beginning. Like, can we support, you know, a state-of-the-art deep learning framework right now? And if we can't, like, let's fix this while things, you know, while the cement is still wet, right? Let's use this really as an opportunity to co-design the actual communication library itself with with an actual use case, and where, you know, the end goal is to have this, you know, in a production environment. So we set about and put together basically kind of a three-phase approach. And the first phase was really sort of demonstrating the proof of concept. So we started this, I think it was either at end of July or August, kind of really from scratch. We didn't really have anything except sort of an idea of what we wanted to do. We had a lot of building blocks with XCCL that we were using for data-driven design choices. This is, you know, sort of a philosophy that we have in my group. Like, you know, we don't do anything in a vacuum, and we don't pontificate, you know, on a whiteboard about, you know, what an API should look like. I mean, we actually build prototypes, and then we try things, and, you know, we take things that we know have worked, things that we don't know that work. We do a lot of experimentation, but it's in the context of actual real code running on, you know, real production scale systems. Like, we're not doing any kind of, you know, we think this might work. And so, you know, I mean, we're big blocks moving these things around. So we were able to, you know, sort of rapidly prototype this together in about, you know, 3-4 months. And so phase one, and so we're checkpointing, the due date is December 2020, the due date is today. So, you know, basically we gave ourselves this talk as an opportunity to sort of checkpoint the work and then see what makes sense, you know, from the perspective of going into phase 2 and into phase 3. So phase 1 work, you know, is implement a Torch UCC, PyTorch UCC process group. We did that as a third-party plugin, so that gave us the ability to be flexible. Like, we didn't want to push something or try to get something committed into PyTorch core that, you know, for an API that doesn't even exist yet. So we did the Torch UCC as a third-party plugin to PyTorch as, sort of a vehicle to rapidly just get things going. And, we'll take UCC as the API as it is, and which is now, sort of fully hardened. But, and the goal would be to support as Srinivas laid out, the goal is to support a single UCC process group that can transparently support GPU and CPU buffers for all reduce and all to all. I'll get into the sort of the details. We don't need to cover that quite so much yet, but basically, the bottom line is really the idea is to use UCX for all to all. And add support for UCC in Facebook param.com's benchmark suite. So the benchmarking package that Srinivas and his team and others in Facebook have released, as this nice diagram demonstrates, right? So params sits on top. Params is a PyTorch based benchmark that kind of looks like OSU, but it's more DLRM-esque. So it sits on top and uses the process group, so we can experiment with different backends and see what different backends look like and benchmark different strategies for the process group. So the support needed to be really added to that because, initially params only supported, I think it was nickel and glue and MPI backends. And so now, in collaboration with Facebook, Srinivas and his team have added support for UCC, which is amazing. And we're able to run param with UCC, just like we can run param over nickel, for example. Next is to support, so we want to give proof of concept that we can support GPU, CPU, and a preliminary POC level support for DPU. So we want to be able to actually execute under a single process group. Can we do a GPU-based all-to-all, a GPU-based all-reduce, CPU-based all-to-all, CPU-based all-reduce, all in the context of a single UCC process group. So we needed to demonstrate that proof of concept as well. We wanted to, and we don't want these to just be like toys. The idea here is that these are production grade, military grade pieces that we're piecing together. And the goal here is to absolutely push this out onto the biggest scale that we possibly can early on and evaluate it. So we just started looking at 256 GPUs with param comms and DLRM on Selene. So Selene is NVIDIA's DGX Next A100 SuperPod. I'll get into that, to the architecture there in just a second. And then simultaneously, so the work that's happening in NVIDIA, Facebook is tracking along, we're marching arm in arm, and they're deploying the software, the same software that we're deploying on Selene, they're deploying in their production environments and evaluating and experimenting with it as well at scale in their environments as well. So that's this is phase one. This is the checkpoint. So we're turning in our homework today, and the goal for so the phase one deliverables. So we're turning in our homework. So the phase one deliverables, these are all the elements that encapsulate everything essentially for all phase one completion. So everything, it exists today on GitHub, either on Facebook Research GitHub or on OpenUCX GitHub. And there's nothing that isn't available. Like, you can take this and you can do the same experiments that we did today out of the box, pretty much on any platform that supports UCX. CPUs, GPUs, doesn't matter. The phase two joint objectives. So we're going to put down some concrete milestones here. Again, this aligns, with NVIDIA's, this aligns with NVIDIA's delivery schedules, essentially, sort of aligned with our POR. So joint objectives, so joint being Facebook and NVIDIA, we have a joint objective due date for phase two, which would encompass a stable UCC v1 API, which I think everybody seems okay with. Transitioning XCCL, which is a prototype implementation of the draft UCC v1 API, at least just the small little pieces of it that we're experimenting with. XCCL, so transitioning those pieces, everything that sits in XCCL is, on its way into UCC core, one way or the other. And UCC V1 GA release that can support all reduce and all-to-all with GPU, CPU, and some kind of alpha level support for DPU as well. And then we'll validate the performance and scalability with param comms and DLRM on Selene full scale and deploy in production in Facebook. A phase 3 joint objectives would be, getting another 2 feature releases out supporting all reduce and all-to-all, really kind of a full support, full-throated support for GPU, CPU, DPU, support for NDR offloads. This is on the NVIDIA side, so things like Sharp v3 and the all-to-all offloads. And then working on some of the not as sexy stuff, but what actually makes it usable in production. So providing best out-of-box experience. So the selection logic doesn't have to be managed by a machine learning application consumer. All of the selection and algorithm choices that are made and team selection happens automatically under the covers, just the way it does for HCall today. And again, validating performance and scalability with params and DLRM on Selene as sort of a reference architecture for a state-of-the-art machine learning, sort of exascale class machine learning, deep learning architecture. So I'm going to go ahead and just sort of dive into, sort of the technical work that we did. So the measurements that we'll be presenting, this is on the Selene SuperPod. This is NVIDIA's DGX Next A100 supercomputer. It clocked in at number 5 on the top 500 last month. It's 256 nodes. Each node looks like this here. So you have 8. It's a real beefy machine here, right? So you've got 8 ConnectX 6 HDR InfiniBand enabled HCAs, 8 A100 NVIDIA GPUs, 2 AMD CPUs with PCI switching and NV switching. And so this is what the inside of the node topology looks like. So every GPU can talk to every other GPU through the NV switch. Every GPU has like an affinity to a particular HCA. So this GPU has an affinity to either of these 2 GPUs, so on and so forth. I mean, you see the basic flow here. The CPUs here, there's a single link here. This is a single 200 gigabit link that these 2 will share. Each GPU has its own 200 gigabit link into an HCA. This is it's a quantum IB switch, so it's HDR switch, and actually this is sort of something interesting. So those 8 rails are actually organized in the fabric according to what we call a rails optimized topology. This is something that was designed in essence to be Sharp friendly, and so in order to allow Nickel to use Sharp for all reduce and enable, enable Nickel to use Sharp for all reduce at full scale and get full bandwidth on all rails and manage the very limited amount of Sharp resources that are actually available in the switch. So this leads to this, topological design, right? So that's actually something pretty specific to a feature in the switch. We actually don't have any real topology, the all-to-all that we implemented for this work. It really isn't even aware of this topology. So that's something I'll kind of call out, like we have this topology, it's complicated topology, something like nickel gets this full vision of everything on the node and outside of the node. And it does, creates these really, elegant schedules. And this is something that we're missing in UCC, I'll say. There's no way that we can sort of tease out and figure out, what kind of a topology am I sitting on, and does it make sense to do sort of execute a different type of all-to-all collective schedule? Even if it's a pairwise exchange, maybe you would do it, maybe you might do the index labeling of the pairs that you trade with in a different way based on just even knowing something about the Rails optimized topology. But this is something that we're missing. But the all-to-all and all-reduce algorithms that we exposed through the team's abstraction. So we implemented just a basic UCX team. So now we're just using building blocks, just the UCX UCP API to build, do very simple pairwise exchange algorithm for all-to-all. And we threw a little flair in there with adding a chunk, which we can, so we'll walk through it. So a chunk means a chunk size greater than 0 means there's chunk number of UCX messages in flight. So instead of doing one pairwise at a time, you issue chunk number of pairwise exchanges simultaneously and do them in batches like this. And again, all of this code, these are really quite straightforward protocols, and we actually just scoop these things out from HCall because we already implemented them there anyway. So the all-to-all pairwise chunk, all reduce is just, it's a scatter, reduce, all gather. And again, in HCall, we support, we can do the all reduce on GPU buffers, and we launch a kernel to do the compute for the reduction phase. So I mean, we have some basic GPU support to support GPU-based all reduce in our UCX team. One of the interesting things about the UCC interface and the team's abstraction is it basically allows you to sort of mix and match different libraries as a whole, like treat these as sort of objects and really be sort of a coordination and orchestration layer, shuttling data between the two libraries through some dependency graph. So that means that we can do things like add a nickel team. So we did this in HCall as well. So when we wanted to get like sort of poor man's GPU support, and we didn't really know anything about GPUs, and 5 years ago or so, we just implemented a nickel B call in HCall and said, well, now we have GPU support. So we just layered HCall on top of nickel, and boom, all of a sudden, we sort of had some kind of basic functionality GPU support in HCall. And this is the same concept. So we implement a nickel team, which means basically it's UCC sitting on top of nickel. And we're using latest 2.8 for all reduce and all. This just gives us sort of a way to get to ground truth with respect to GPU performance. Nickel is the best in class from our perspective in terms of collective communication performance over GPUs. So this should give us ground truth. We're going to use this simply as just sort of a measuring stick to understand how well we're doing with respect to the UCX stuff. We've also implemented a hierarchical team, so we want to sort of demonstrate some of the advanced functionalities where we're actually using different teams and orchestrating them to affect an all-to-all operation where we're using nickel on the host. So utilizing all of the goodness of nickel for NVLink communication, and then utilizing UCX for the scale out communication. And in a single all-to-all call, sort of mixing those two together so that, when you're doing an operation that goes to a pure GPU on a node, it's going to call into the nickel team. And otherwise it'll call into the UCX team. So this is the data that we've generated. Now I'm going to just sort of say, like, this is not this is not peer reviewed. This is like data that's coming in, rapid fire. We know what speed of light looks like. So speed of light is somewhere like around here. And so what we want to demonstrate here is just basic functionality. We want to demonstrate basic functionality and show that we're feature complete, and then discuss strategies for next steps for optimizing. So I see that we've completely run out of time here. So this, we have all-to-all on GPU. I think, the piece here that I want to get out is, sort of what the command line looks like and sort of how it still feels like a UCX command line, right? You have your UCX TLs, you're specifying, for GPU, you're going to ask for your CUDA transports. You select a Torch UCC, we call it a TLS right now. And we're selecting the UCX team. So this is the team. I guess T in this case means team library selection. And this is actually the params, the Facebook params.com benchmark, specifying what type of compute device to use. So in this case, you're using a CUDA device, and what backend. This is the UCC backend for the params.com that was added. So that's really neat to see UCC as a backend to params.com. This is the params.com benchmark on all reduce over GPU. Over GPU buffers. This is the UCX team. This is the nickel team. Obviously, we would expect the nickel team to do better than just a scatter reduce all gather. We're not we don't have all of the nitty gritty NVLink orchestration that happens at the nickel level for their aggregation phase on the reduction. So again, nickel here is ground truth, and this is, this demonstrates proof of concept that we can do this. And then, the next phase is optimizations. Param.coms, we have all-to-all now. So again, the homework assignment for phase one is we have to demonstrate, all-to-all and all reduce with GPU buffers and CPU buffers. This is that demonstration. So again, this is param.coms. So using the Facebook param.coms benchmark, running over the UCC PyTorch process group, and invoking the collectives in XCCL. And in this case, you can see the device here is a CPU device, backend is UCC. It's the same Torch XCCL team library, it's UCX. We can't use nickel here as a comparison because nickel doesn't support CPU buffers. So we're just, this is just UCX against itself for different chunk sizes. This is just doing a simple parameter study and just looking at just some scaling characteristics and algorithm tuning. And same thing with all reduce. Again, this is CPU based all reduce in XCCL. We threw glue in here just to see what would happen, just as a sort of a checkpoint on Selene, and just to give us something to compare against, because we didn't obviously we don't have a nickel, nickel to compare. So I was going and trying to say, okay, well, where would I fill in, on Srinivas's table? If I had to do the selection logic, I mean, does it go and it fall back onto like a glue, all reduce on a CPU? So I think, that's probably what would be used in production today. I don't know. And then the last thing is to actually be able to run DLRM on Selene. So now, we've turned in all of our assignments. We can support GPU buffer, CPU buffer. We're getting near speed of light for both of those protocols. And now we're able to actually run DLRM really essentially at any scale. We don't really know what this is. This kind of just came fresh off the presses this morning. So, but bottom line, we're able to run DLRM on Selene. We can essentially do this at any scale. There's nothing that prevents us from scaling this up to full machine scale. And then, this just gives us, all of the tools, the profiling tools that we can use to just show, where is time being spent. So this is how we plan to start, this is sort of a segue into the next phase of work, which is now we have functionality. Next phase is, doing the optimization, and then a lot of the unsexy stuff that gets something ready to be put into a production environment. All of the QA and adding the support for different flavors of MoFed and so on and so forth, and different CUDA runtimes and all, the unsexy work that actually ends up making, something production grade. So with that being said, I put out some pain points. Since we're so far over the head, I thought we would have time to talk about this, but there were multiple pain points that we, discovered in this work that, one way or the other, we need to address these pain points. But, that's the focus of the work going forward. So with that being said, I don't want to cut into Megan's talk. So why don't we go ahead and go do a quick round of questions.
Yes, we have a couple of questions pending. It's actually nice to see some of the pain points overlaps with what Alex presented earlier. So there's a few questions in the chat. Maybe people, instead of me reading it, unmute and go ahead and ask. Alex?
Yeah, sorry. I actually got answers to my questions over the talk, so I'm good.
Any other questions for Josh?
Or
actually, I have a question for both Srinivas and Josh. So it seems like the pain points that you are calling out here, right? UCC being stream aware. I think that is quite clear to us, as I mentioned earlier in the talk today, right? We are aware of this requirement and we definitely appreciate it, but we haven't got a chance to address that. So we'll go to address that, right? We should have a solution. There's no. What's interesting for me is canceling a request, right? Abort. This is kind of a very tricky to implement, even for just a one endpoint. Can you guys lay out like where and how you see this, and what's the semantics you would like for this?
Manju, since we over the time,
sure.
Can we take it this question offline?
Yes, definitely. I think it might be more deeper question than I wanted. Sure, no problem.
Josh and Srinivas, thank you very much for attending and presenting. Really appreciate it. Really interesting presentation.
Thank you.